You're listening to Paranormal Optimist. My name is Stephanie, and in this podcast, we dissect paranormal topics from the perspective of skeptics, believers, and everyone in between. At the end, it's up to you to decide. Are you a paranormal optimist? Welcome to the first episode of Paranormal Optimist. Before I dive in, I just want to take an extra minute right here to thank you so much for giving this show a chance. I know how valuable free time is, and you're choosing to spend it on this random show from a random woman who's obsessed with aliens, cryptids, and ghosts. Let's get to it. When I finally made the leap and started producing this show, I had to think about where I personally would begin telling this story of the paranormal. This is the thing. If you're friends with me, I only bring a few things to the table. 1, I will yell paranormal facts at you. I won't do it on purpose, but it is going to happen. 2, I will send you unsolicited pictures of the moon. No context, just the moon. I consume everything I can find that is spooky adjacent. Tell me your ghost stories, your cryptid sightings, your weird and ineffable experiences. Seriously, please tell me them. paranormaloptimist@gmail.com. But when I boil it all down, the only possible starting point for me really is this essential question. Are we alone in the universe? Here is my bias on this topic. I have spent my entire life looking up at the night sky, not wondering, not believing, not even hoping, but knowing that somewhere out there, someone else is looking back. The thought that we could be it, the be-all, end-all of all complex life in the universe, a universe that is so vast that our brains can't even truly comprehend its size, makes absolutely no sense to me. My brain straight up rejects that thought. And I know that's not scientific, but I am not a scientist. I do have a master's degree in history, and for some reason, I also have a master's degree in business. I spent my undergrad studying foreign language, and my entire career has been in education and healthcare services. All this is just to establish the fact that I am not an authority or an expert on this topic. I'm an optimist. So, of course, since this is the mindset that I bring with me when I approach researching this topic, I'm going to interpret the data in a way that subconsciously supports my belief, because that's how biases work. The way to mitigate the effect your biases have on your overall worldview is to be aware of them and to learn as much as you can from as many different sources as possible. So throughout this show, I will try my best to keep my mind open to whatever the truth may be. But please know, I will always want to believe. Here's what you can expect from today's episode. We'll open with a brief history of science in relation to people wondering whether or not we are alone in the universe. We'll follow that with an overview of the reasons why people do not believe in the possibility of extraterrestrial life. After that, we'll discuss how and why others do still believe, even in the face of such compelling opposition. We'll follow that with a discussion of where to go from here. Now you know why people do believe or don't believe, but what do you do with that information? We'll discuss the work that skeptics and optimists are doing to try to prove their arguments. Let's get started. So let's talk about the history of people wondering if we are alone in the universe. The thing is, when you research this topic, nearly every book tells a generally similar story about the history of science. The main theme always being that we got it wrong, over and over and over again. It is a story of people clinging desperately to comfortable beliefs and choosing to murder those with novel ideas rather than accept the vulnerability of the unknown. It was a violent and chaotic interchange between the warring factions of tradition and truth. I mean, even if you think about it in today's climate, most people who say that they have had a paranormal experience, such as seeing a UFO or a ghost or something like that, face a certain level of public humiliation. In our current society, we have been trained very well to laugh when presented with this possibility. Although, I do admit that moods do seem to be shifting lately, but that is a topic for a different episode. As we will discuss, however, things used to be much worse for those who chose to explore the unknown. To emphasize the dramatic nature of humans in the face of the unknown, let's talk about a few facts that we now take for granted. We live on Earth. Earth is a planet, and it's actually the third planet in a system of planets, which all orbit the sun as a focal point. If you have read books on this topic or watched programs hosted by popular scientists such as Carl Sagan or Neil deGrasse Tyson, you will have heard the following stories already. But here are just some examples of humans being murderously wrong in the realm of basic scientific understanding. Nicholas Copernicus is an easy starting point for this discussion, as he is an example of a person who suggested ideas that were radical for his time, yet today are completely correct and totally benign. He is best known for asserting that the Earth was a heavenly body which orbited the sun, and that there were other heavenly bodies also orbiting the same sun. This went against the belief system, which placed the Earth at the center of creation. He is also credited with discussing the idea that the cycles of day and night experienced on Earth are due to the rotations of the planet on its axis, and are not the result of any supernatural or divine influence. While ridiculed in his time for these theories, Copernicus had the somewhat good luck to die of natural causes in 1543, shortly after publishing his work. The next example I will discuss was not as fortunate. Giordano Bruno was influenced by Copernicus and agreed that the Earth was neither figuratively nor literally the center of the universe. Other theories of his included arguments about the infinite quality of the universe, the possibility of the existence of other planets, and perhaps even other life forms in other parts of the cosmos. He was burned alive in the year 1600 for refusing to renounce his many beliefs, which were incompatible with the religious powers at the time. Galileo Galilei publicly argued and defended his theory of the heliocentric model of the solar system, which was supported by both the works of Copernicus and Bruno, meaning he also argued that the Earth orbited the sun and not the other way around. He was condemned by the Roman Catholic Church and sentenced to house arrest in 1633. He eventually died 8 years later, and this condemnation was not officially redacted by the Church until 1992. Science, of course, has come a long way. We now have reached the point of the script where I will allow myself to quote Carl Sagan. But first, let me head this off by saying that I madly respect Sagan. And I do understand that he certainly never anticipated his words to be used in a paranormal podcast. He was a brilliant and reasonable man who taught an entire generation of people the validity of science. So please take his words at face value and don't confuse my beliefs with his. So here is a quote from one of Sagan's most popular books, The Demon-Haunted World, Science as a Candle in the Dark. At the heart of science is an essential balance between two seemingly contradictory attitudes, an openness to new ideas, no matter how bizarre or counterintuitive they may be, and the most ruthless, skeptical scrutiny of all ideas, old and new. This is how deep truths are winnowed from deep nonsense. And this is generally how we view science now. We are more comfortable with asserting our ignorance. We understand that science must be conducted systematically and committed to testing, experimentation, and observation. A belief can be a starting point, but only investigation based on evidence can lead to meaningful explanations. Yet, when it comes to certain topics, such as those which will be covered throughout this show, we still have some academics bursting from their lab coats in a frenzy to declare that something is impossible. For this, I serve you another quote from Sagan. The cure for a fallacious argument is a better argument, not the suppression of ideas. And that's another one from the demon-haunted world. So, my request to those scientists who are continuously dropping their monocles is this. Yes, tell me I'm wrong, but tell me why I'm wrong. I'm fine being wrong, as long as it's the truth. Give me a rebuttal that makes sense, is provable, and isn't more outlandish than the paranormal argument. I'm listening. Why not to believe? The Fermi Paradox. One of the topics referenced most by skeptics, whether they be academics, experts, or laypeople, is the Fermi Paradox. In keeping with my theme of transparent biases, I will admit here that I legitimately hate the Fermi Paradox. If I'm being completely honest, it fills me with rage. But more on that later. First, let's discuss who Enrico Fermi is, what the Fermi Paradox is, and why so many have been so comfortable with allowing it to prevent them from intellectually considering the question of life elsewhere in the universe. So, who is Enrico Fermi? Among many other accomplishments, he won the Nobel Prize for Physics in 1938. According to the Nobel Prize website, the reason that he received this honor was for, quote, his demonstrations of the existence of new radioactive elements produced by neutron irradiation and for his related discovery of nuclear reactions brought about by slow neutrons. Now, as a layperson, I have no idea what that means, but the website goes on to explain that his discoveries ultimately became a tool for furthering the study of atoms. And as a history buff, I do understand the significance there, because it was in his lifetime that the world saw the advent of atomic weapons. So furthering the study of atoms would have been of the utmost importance during this time. So basically, Enrico Fermi was generally considered to be a genius in the realm of science, and specifically in the realm of physics. So, I have established who he is and why people have good reason to trust his assertions. But what is the Fermi Paradox? The story goes that this idea originated from a casual lunchtime conversation between colleagues at the Los Alamos National Laboratory in 1950. This nuclear weapons lab is where Enrico Fermi worked at the time. So on this day, in 1950, it's said that Fermi and his peers were discussing the topic of UFO sightings and whether these objects could be seen as proof of the existence of complex extraterrestrial life or civilizations. It was during this conversation where the possibility of abundant and common complex life in the universe was discussed that Fermi uttered his now famous quote, "But where is everybody?" That is essentially the Fermi Paradox. If the universe holds an abundance of complex life capable of interstellar travel, where are those travelers? If faster than light travel is feasible, why haven't we accomplished it on Earth or met anybody else who has accomplished it? Basically, if there are other life forms out there, we should already know about them, because they should already be here. Skeptics, of course, ran with this line of thought, and they continue to run with it to this day. We have no proof right now, so therefore we are alone. The end. No more thought, research, or discussion needed. Because that's how science works, right? And with that bit of sarcasm, I come to why I personally hate the Fermi Paradox. It's a casual line that emerged from light conversation between coworkers. It is not, and should not be thought of as, legitimate proof that we are alone in the universe. And I'm sure that Fermi never even intended it to be taken as such. It is a great question, but where is everybody? But there are so many explanations for why we may be currently unaware of others like us who may exist elsewhere. I am not going to go over every rebuttal to the Fermi Paradox. It's been over 50 years. There are so many rebuttals out there. The two most well-known rebuttals to the Fermi Paradox I will discuss here, though, and they are the Great Filter Hypothesis and the zoo hypothesis. The Great Filter Hypothesis. This essentially means that there may be some barrier in the rise and development of life that makes it extremely difficult for civilizations to emerge and survive their own self-destructive tendencies long enough to develop the technology needed for interstellar travel. Now, that was a bit of a mouthful, but basically, these barriers could be natural, such as there being no power source which exists that could make this technology possible. They could also be social barriers, in that civilizations inevitably destroy themselves or their planets due to their own development. So maybe we aren't the only civilization that has ever existed in the universe, but we might be the only one that exists right now because prior civilizations may have already destroyed themselves. And even if we aren't the only one that exists right now, we may never discover otherwise due to these barriers. The zoo hypothesis. This hypothesis operates under the belief that there definitely are advanced civilizations out there. Maybe there's tons and tons of them out there, but they are deliberately choosing not to interact with us. Obviously, we have no idea why that would be the case, but the common opinion among those who follow this hypothesis is that we have not yet achieved the level of technological advancement necessary to be deemed worthy of contact. If you're a fan of Star Trek, which you should be, this sounds familiar, right? Because it is the basis of the Prime Directive. All of the rules and regulations surrounding first contact in that fictional universe. Beings who are capable of faster than light travel are ignoring us, because to them, we are just an example of lesser and primitive animal life who still has to progress to a certain point before they can contact us. So those are just two of the rebuttals to the Fermi paradox, and as I said, there are many, many others out there. If you're interested in learning more about the other answers to the Fermi paradox, you can find a lot of information just by Googling the phrase Fermi paradox solved, the rare earth hypothesis. Another reason that skeptics cite when arguing against the possibility of other complex life in the universe is the idea of the rare earth hypothesis. This idea is actually quite interesting because it's also cited as one of the solutions to the Fermi paradox as well, but definitely not in an optimistic way. Considering how much I hate the Fermi paradox, I went into my research of the rare earth hypothesis fully expecting to feel the same level of animosity. But that's why it's good to be aware of your biases and try to overcome them. Because I surprisingly found the rare earth hypothesis to be fascinating. And unfortunately for me, somebody who really wants to believe, I also found this hypothesis to be very rational and logical and plausible. So, what is the rare earth hypothesis? The essence of this argument is right in its name. The earth is rare. Complex animal life is rare. Our planet is incredibly special because a series of processes happened in exactly the right way, under exactly the right conditions, and with exactly the right timing to allow Earth to evolve and prosper in the form we know today. The basic idea is that the evolution of life on Earth, the process which allowed for the rise of single-celled organisms and their eventual adaptation into complex animal life over billions of years, happened as the result of countless variables, colliding and interacting in specific and seemingly unpredictable ways. It was a process that was so complex, so convoluted, and so random that it is highly unlikely that such a scenario could have played out again in exactly the same way somewhere else in the universe. To put it simply, we are lucky to exist. So what made life as we know it on Earth possible? Here I'll discuss a list of just some of the things that are true of Earth, which contributed in different ways to the emergence of complex animal life. Earth is located in the habitable zone of our star, also called the Goldilocks zone. As the name implies, we're not too close, we're not too far, we are in just the right place. And being in this place makes liquid water on the planet's surface possible. Earth also has just the right mass, which makes it able to sustain an atmosphere, liquid oceans, and a molten core. Earth has plate tectonics, which promotes biodiversity, biological productivity, temperature regulation, and also enabled the formation of both land masses and bodies of water for life to thrive. Earth orbits a star with a stable mass and a long lifespan, which gave life the time to emerge and develop. Earth has an early history characterized by being bombarded by objects from outside of the habitable zone, which delivered things like carbon, nitrogen, water, and amino acids to the planet's surface. Earth may exist in just the right place for life to thrive, but these building blocks of life existed in the outer limits of the solar system. Earth has a friendly neighbor in the form of gas giant Jupiter, which prevented bombardment from objects large enough to destroy the planet. These larger objects were captured by Jupiter's extraordinary gravitational pull. So basically, Earth had the amazing luck to be hit by smaller objects, the smaller objects that were carrying the essential elements of life, but it was never struck by objects large enough to prevent that life from forming. While this list deals primarily with the location of the Earth in the solar system, as well as its physical composition, there is another aspect that lends to the theory that Earth is rare in the universe. The evolutionary process that life on Earth underwent was a complex and difficult phenomenon. The eventual shift from bacteria to complex animal life was a process that involved periods of stagnation and great leaps forward in response to specific environmental changes, such as ice ages and other climate shifts, which affected things like ocean chemistry and surface temperatures. The point here being that, since evolution is a long process of multi-generational adaptations to changing conditions, there is no reason for us to believe that life would develop in the same way on another planet. Life here developed in exactly the way it needed to in order to survive on Earth specifically. With such a compelling argument, how can I still be optimistic about the possibility of life beyond Earth? As rational as the rare Earth hypothesis is, the key word to remember here is rare. Claiming that complex life, such as that found on Earth, is rare does not mean that it is non-existent elsewhere. It just means it's probably not common. The biggest problem with using the rare Earth hypothesis to claim that we are the only complex life in the universe is that we are the only example we have of complex life. And I know that sounds like circular logic, so just hear me out. We have nothing to compare ourselves to, and we don't currently have the technological capability to rule out the possibility of life in other parts of our galaxy, and certainly not in even further reaches of the universe. We don't have enough data. We can't come to any definitive conclusions. We do know that Earth is certainly rare in the dataset that is our own solar system. Extrapolating further without any concrete evidence of what exists outside our neighborhood that we are able to observe is simply just a thought experiment. It may be compelling, like the Fermi paradox, but it's not proof of anything. When you think about the difficulty that life had emerging and evolving and eventually thriving here on Earth, it is so easy to just say, no, there's no way. It can't happen again in the same way. But that's the thing. Why would it need to happen in the same way? The progression on Earth was amazing, and it was due to so many incredible variables. Earth was lucky to be in the right place at the right time and to have the protection granted by other planets, which were also in the right place and at the right time. But what if that's not how it is for planets orbiting other stars? What if there are other solar systems out there that are just better suited to life? And maybe life is always a complex and difficult process, but maybe it doesn't always face the same level of adversity in all parts of the universe. A question we should also be asking is this: even if life that is similar to ours is rare, does that mean life itself is rare? Remember that the life that evolved here adapted specifically to the conditions of this planet. Logically, life in other environments, if it exists, would have an endless range of evolutionary possibilities and may not even be recognizable to us as life at all. Ultimately, that's why I'm still optimistic. Earth is the only example we have, but it does not mean it's the only possible route for life to emerge. And my favorite thing about the rare Earth hypothesis is this: the only way to prove it is to keep exploring the universe. Why to believe? Despite how my script has read so far, This episode is actually not intended to just be me yelling at highly educated skeptics who won't let me have my aliens. Luckily for us, there are actually plenty of experts out there who are cautiously optimistic about the probability of life existing throughout the universe. And I'll take cautious optimism over blind skepticism any day of the week. So, let's look at some of the reasons why we can all feel better about wanting to believe. The Drake equation. A lot like the Fermi paradox, the Drake equation is a thought experiment which has caused a lot of drama in the debate over extraterrestrial life. I personally used to dislike the Drake equation almost as much as I hated the Fermi paradox. That was until I realized that I, just like many others, had completely misunderstood how the Drake equation actually works. I chalk this up in part to my lifelong and fatal inability to understand math. It's a real problem. So before we get into breaking down the actual numbers, which believe me, I am citing the work of others and not my own, let's talk about what the Drake equation is and where it came from. Frank Drake was a true pioneer in the systematic and evidence-based search for extraterrestrial intelligence. An astrobiologist and astrophysicist, Drake drove innovation in the field of radio astronomy by using radio telescopes as not only a method for studying things like the composition of planets and stars, but also as a means to search for signs of intelligent life. Through his pioneering work through Project Ozma and SETI, Drake led the search for signs of intelligent life by scanning for radio signals that were not of natural origin. Basically, this was the start of humanity's search for hints that someone out there was trying to communicate with us. As is unfortunately the case for most endeavors of this nature, Drake and his colleagues faced significant challenges in the form of political opposition. In the 1960s, it was not an easy existence to be a serious scientist who was also open to the possibility of alien life. Drake had to find a way to help academics, lay people, and unfortunately, politicians conceptualize the validity of searching for life outside of our solar system to legitimize the financial demand of these projects. The result was the Drake equation. Drake developed his equation to determine how many advanced technological civilizations existed in the Milky Way galaxy. It was by intent an extremely specific question that Drake hoped would simplify the task of creating a true framework for searching for intelligent life. In Drake's definition, advanced technological civilizations would be those that could participate in interstellar communication via radio transmissions. The Drake equation basically tells us the probability of this type of life existing based on several variables with both known and unknown values. To my utter horror, Drake turned the search for aliens into a math problem. The variables in this equation, and I do apologize because this is incredibly hard to describe in an audio format, are the number of stars that form each year, the number of said stars, which have planets in their orbit, the number of those planets per system, which are in the habitable zone, the number of those planets where life actually forms, the number of those planets where life was able to evolve from simple life to complex life, the number of those planets where the complex life evolved into technological civilizations, and finally, the average lifespan of those civilizations. In the equation, each variable is multiplied in succession, with the solution being the number of advanced civilizations detectable via the use of radio astronomy. As may or may not have been clear by my feeble attempt to break down the components of the equation, we start with a huge variable, the number of stars in the galaxy, and continuously chip away at it by multiplying it by increasingly smaller values, sometimes which are fractions of numbers. Some skeptics argue that the Drake equation supports the unlikelihood that life could exist, due to the result being such a small number or zero. But does it really mean that? One problem with the Drake equation is that we do not actually know the values for most of the variables. So, depending on who is working the equation, values could be used which lead to a result which supports either their bias as an optimist or a skeptic. For example, if you believe that any of the values are 0, that basically breaks the equation for the optimist. On the flip side, if you overinflate any of the unknown values, you are left with a solution that is wonderfully, yet probably inaccurately, positive. I really would love to just insert the audio here of Carl Sagan explaining the equation, because he does it so clearly and in that special way that he describes everything so easily for a popular audience. I have absolutely no idea if that's legal, so instead I hope you'll take a few minutes to find it and listen to it, because it's pretty wonderful. You can find the breakdown in episode 12 of the original Cosmos, and the name of the episode is Encyclopedia Galactica. But my takeaway from his explanation is this. Life can be both rare and abundant. Those two things can be true at the same time. And the reason for that is the mind-boggling number of stars that exist in the universe. To try to conceptualize that number, think of it like this. It's currently believed that there are hundreds of billions of stars in the Milky Way galaxy alone. Any number of those stars could host a system of planets. The likelihood of that depending on the age and type of star, among many other variables. But again, hundreds of billions. A conservative estimate regarding the total number of galaxies in the universe is somewhere around 1 trillion. I've even seen some say that it's probably closer to 2 trillion. If our single galaxy hosts hundreds of billions of stars, we can't even comprehend the number of stars existing across all galaxies. So even if the number of planets is smaller, and the number of habitable planets even smaller, and so on, it seems to me that we are still left with a positive number at the end of the equation. The probability then, in my opinion, is not only that there is life, but there is lots and lots of it. The question as to whether we will ever see or have ever seen evidence of this life is the topic for a different episode. What now? So far, we have touched upon the various reasons for why people either do believe or don't believe in the possibility of extraterrestrial life in the universe. In my opinion, both sides of this debate really do have valid points, even if I'm still firmly an optimist. But where do we go from here? What do we do with this information? So, in this section, I will talk about some of the work that people are doing to try to prove their arguments. How would we find life? The search for life off Earth is both exciting and frustrating. Exciting because there are actually multiple methods and routes available to us right now with our current technological capability. Experts even seem to be quite optimistic about our ability to start collecting new and meaningful data and potentially begin making some amazing discoveries. It's frustrating because even after all this time, not everyone in the position to make decisions agrees that the undertaking is worth expending the resources, both in manpower and financial funding. So, for the purposes of this conversation, let's just take the politics out of it, something I prefer to do in all parts of my life, and talk about how we could find life or hints of life if the resources were not an issue. Planets. For a lot of people, the idea of there being life out there obviously means that there are other habitable planets out there. It's a simple correlation, and it's the basis for the work of many scientists today. So in a way, one starting point in the search for life would be the search for habitable planets. Here's a historical fact that's relevant and amazing. The first extrasolar planet, or exoplanet, was not officially recognized until 1995. Please let me say that again. Until 1995, we did not know with any certainty that there were any other planets at all behind the 8, RIP Pluto, that make up our own solar system. To put that in perspective, that is the same year that saw Toy Story, the first computer-animated feature film, and the launch of things like PlayStation, eBay, and Amazon. Within only a few months of this discovery was also possibly the most influential and defining event of my life, the Japanese release of Pokemon Red and Green, or Red and Blue for us later on in America. My point with this possibly annoying tangent is how modern this discovery is. Since 1995, thousands of planets have been confirmed to exist outside of our solar system. At the time of this writing, over 5,800 planets have been discovered. So we went from 0 to nearly 6,000 in only 30 years. Of course, scientists suspected that exoplanets were a possibility long before this, with some pioneers questioning and attempting to prove this as far back as John Goodricke in 1784. He was the first person, to my knowledge, to notice and track the periodic dimming of stars, which we now know is caused by orbiting objects, namely planets, passing into our view. And obviously, looking at science fiction, which existed well before 1995, you can see a public consciousness that accepted the logic that there had to be other planets out there, even if we didn't have the ability to prove it yet. So, how do we find a planet? A great starting point for learning about this topic, if you're a layperson like me, is NASA's official page about exoplanets. Go figure! On that page, you can find the 5 methods currently used to locate and identify exoplanets. Those 5 methods are this: radial velocity, transit, direct imaging, gravitational microlensing, and astrometry. I highly recommend checking out this page. NASA has created visual aids, which as an educator I really appreciated because they were highly effective at conveying the definition of each method and how it differed from the other techniques used to locate planets. Radial velocity. This method is described as watching for wobble, meaning astronomers are watching stars for movement called wobbling. The movement of a star indicates that it is participating in what NASA calls gravitational tug-of-war with an orbiting object. So while the star would definitely have the more powerful gravitational pull, which is what causes the planet to orbit it in the first place, a planet actually does pull back a bit as well. These tiny movements in the star's position are what scientists are looking for. To date, this method has helped to identify 1,100 planets. Transit. Using this method to find planets involves searching for shadows. Quite simply, this method involves monitoring stars for signs of observable and measurable dimming to the light they emit. This dimming could be caused by a planet or some other orbiting object, passing into the view of our instruments and temporarily obscuring some of the light from the star. This method can get tricky when dealing with stars with multiple planets, but overall it's been very successful, having assisted in the identification of 4,342 planets so far. Direct imaging. This method is definitely the easiest to explain, as it's essentially just taking photos of planets. While simple in theory, though, it's certainly much more difficult in practice. As camera and photo editing technology advances, however, astronomers are able to take better and better photos of stars and manipulate them to reveal hidden objects in their orbit. While not the most successful method, it has helped to confirm the existence of 82 extrasolar planets. Gravitational microlensing. For me, this method was the most difficult to understand. The way it's defined on the website is, quote, light in a gravity lens. Light from the distant star is bent and focused by gravity as a planet passes between the star and Earth. To truly understand this method, I suggest looking up videos of what lensing events look like. For me personally, seeing the videos explained this method better than any written explanation could. But if my understanding of what I have read is correct, lensing events would be these instances of light distorting and changing direction. When observing a star with an instrument, these events would look like bright flashes of light or even noticeable bending in the path of light from the star. This bending and brightening of the light from the star is seen for a period of time before dimming again to the levels and appearance prior to the lensing event. So to summarize or likely better explain this idea, here is another direct quote from the NASA page. In other words, big objects warp the fabric of space. This effect causes light to distort and change direction when affected by the gravity of a massive object like a star or planet. This method has led to the discovery of 235 planets to date. Astrometry. This last method is the most difficult to perform successfully, and is likewise the least successful method used so far to discover planets. At the time of this research, only 3 planets have been discovered using this technique. Extremely similar to radial velocity, this method involves measuring the movement or wobble of a star in relation to other stars in the sky. This technique requires astronomers to take a series of images of a grouping of stars to pinpoint tiny movements of a single star in relation to its neighbors. This movement, or again, wobbling, would in theory be caused by the same game of tug-of-war detected via radial velocity. As technology continues to develop, which leads to better and more precise optics, this technique should in theory become easier and more precise in the future. So, we have found planets which exist outside of our solar system. How do we find life? We already touched upon Frank Drake and the contributions he's made to the field of radio astronomy. It is simply not possible to overstate the importance that SETI had and still has in the search for intelligent life. That's what SETI stands for, the search for extraterrestrial intelligence. It looks for signs of life in the form of radio and optical signals. What started off as a project or group of projects under different names, such as Project Ozma, is now an entire field of science. The idea behind SETI, dating back to a scientific journal article written in 1959, is that if there are intelligent beings out there, they might already know about us. And if they know about us, they may be trying to communicate with us. SETI was founded with the goal of trying to figure out how to find and listen to these communications. In the already mentioned article titled "Searching for Interstellar Communications," the authors argued that intelligent beings who are advanced enough to be aware of us logically should also be aware of our limitations in participating in technological communications. Meaning, if they are out there, aware of us, and trying to contact us, they should be doing so in a way that we should eventually be able to detect using our own technology. Since most of the communications of mankind are detectable in the form of radio waves and microwaves, the assumption was made that these frequencies were a good place to start searching for these signals. This is where radio astronomy comes in. Through the use of instruments, such as radio telescopes, astronomers began listening to the cosmos, hoping that their receivers were aimed at precisely the right coordinates to hear something. Evidence of intelligent life found with this method would be instances of repeated signal patterns, which would appear artificial and intentional in origin. While no undeniable examples of these types of signals have been detected yet, even though some great and compelling things have been found, it doesn't mean that nothing ever will be. The search area, the entire galaxy and universe, is incredibly vast. The search, however, has been continuing on and off since SETI's inception, sometimes funded privately and sometimes by the government, and still continues in this day in an increasingly open source model. So it's a long shot, but who knows? Maybe one day, maybe even in our own lifetime, someone will be focused at the right place and will listen long enough to hear something worth the decades of waiting. Spectroscopy. Another method being used today to search for signs of intelligence is spectroscopy. The Webb Space Telescope website offers a very clear definition of what this is and how it can be applied to a variety of scientific questions. Spectroscopy is simply a scientific method of studying objects and materials based on color. More specifically, spectroscopy involves analyzing spectra, the detailed patterns of colors, wavelengths, that materials emit, absorb, transmit, or reflect. So, what does studying the spectra of different objects tell us? Well, to those who understand how to read these spectra, i.e. not me, they can identify gases in planetary atmospheres, minerals on planetary surfaces, figure out what the stars are made of, how fast they're rotating, measure the temperature and speed of gases in the center of a galaxy, identify black holes and help search for proof of dark matter, and help calculate the expansion rate and age of the universe. So basically, spectroscopy is the skeleton key of tools when it comes to collecting data about basically anything. But how can it be applied to the search for life? What would proof of life look like? When it comes to using spectroscopy to search for signs of life in general, or signs of complex life in civilizations, it boils down to searching for specific signatures. The buzzwords here are biosignatures and technosignatures. What are biosignatures? When discussing the term biosignature, the idea is that there are certain indicators that, if found in the atmosphere or surface of other planets, could indicate that life either currently exists or that it did exist in the past. The existence of certain molecules, which life as we know it needs to exist, such as oxygen, would also be considered an example of a biosignature. This concept came to be as the eventual result of studying our own atmosphere here on Earth. Our atmosphere now is oxygen-rich, composed of about 21% oxygen. Apparently, however, there is evidence that in the Earth's early history, there was no oxygen at all in the atmosphere. So it's believed that life itself is the reason why our atmosphere is now full of oxygen. It's a byproduct of biological processes, such as photosynthesis. So if we found another planet with an oxygen-rich atmosphere, it would be a safe starting point to assume that similar processes, such as those caused by the existence of plants or plant-like life, was the root cause which led to the existence of that molecule in the atmosphere. It would be just a starting point, but it would be a huge hint that life could be present. Finding these signatures in the atmosphere of a distant planet goes back to studying the spectra. Just like we can use spectroscopy to discover the chemical composition of stars based on identifying and matching the way that the spectra corresponds to known elements, we can use the same method, using an appropriately powerful telescope, of course, to study the atmosphere of other planets to discover their composition. Finding oxygen in the atmosphere could indicate the existence of flora or something else capable of photosynthesis. Studying the atmosphere can also tell us things about the planet's surface based on chemical byproducts. For example, the existence of water vapor in the atmosphere suggests the existence of liquid water on the planet's surface. What would proof of complex life look like? While it would be an incredible breakthrough to find conclusive evidence of any kind of life based on locating biosignatures, scientists would absolutely lose their shit if they ever found an example of a technosignature. So, what is a technosignature? I would like to preface this topic by saying that I actually had never even heard the phrase technosignature until I read The Little Book of Aliens by Adam Frank. It's a glorious book, and I've used it as a starting point for a lot of my research for this episode. But apparently this phrase is credited to Jill Tarter, who was a part of SETI in the 1970s. As we already know, SETI's primary focus was, and still is, to search for intentional signals and messages being left behind or broadcasted by intelligent beings. These signals could be seen as technosignatures, of course, and that they would be a sign of extraterrestrial technology. In this way, technosignatures are actually just another type of biosignature, because the thought process is that there can't be technology without life. Or maybe not, but let's talk about that in a different episode. The really exciting thing about technosignatures is that, just like biosignatures, with the right tools, we should be able to detect them, whether they are being broadcasted to us or not. The reality is that life existing on a planet alters the composition of that planet. The same is true of civilization and technology. We should be able to determine, simply by studying the spectra of the atmospheres of distant planets, if civilization or technology is present. Again, going back to our own atmosphere, there is evidence not only of life on this planet, but specifically complex life. Pollution, such as that which leads to excess amounts of artificial chemicals existing in our atmosphere, is the byproduct of our technologically advanced and industrial civilization existing on the planet's surface. Another form of pollution, artificial light, also affects the atmosphere in a visible way. If we saw it on another planet, we would immediately know it was not due to a natural process. Beyond examining the spectra of the atmospheres of exoplanets, there are, of course, other things that, if found, could be considered proof of intelligent life. Let's revisit Earth again to conceptualize this. Our planet is beautiful, it's rare, and it's amazing. It's also completely surrounded by garbage. While writing this, I just did a quick Google search and read that there are currently 2,000 active satellites orbiting Earth. In addition to that, however, there are about 3,000 abandoned satellites out there, which are no longer in use. And that's just satellites. I'm not even going to go into the other idiotic things that people who could sent into space. And if you're interested, there are entire podcast episodes out there devoted to talking about all the trash that is in space and how it's a huge safety hazard, how it's a really embarrassing problem, and how nobody wants to take ownership of it. My point, just for the purposes of this episode, is that this trash, junk, garbage, it exists. If we saw debris like this floating about in space, it would mean everything. It would be an artifact of civilization. It would be the most exciting discovery beyond a close encounter of the third kind that we could possibly imagine. Or maybe that's just me, but give me that alien garbage. Further reading. In writing this episode, I definitely let things get out of hand when it came to how much research I did. The reason why I went so crazy with this research is that I wanted to build a well-rounded and balanced body of knowledge on this topic. So that means I couldn't just read the optimistic books that would confirm my biases. I had to read books by skeptics, too. And I really wanted to, because I wanted to understand how someone could feel so pessimistic about something that I believe so naturally. So here I'll give you a list of some of the books that I read. The Little Book of Aliens by Adam Frank. Rare Earth, Why Complex Life is Uncommon in the Universe by Peter D. Ward and David Brownlee. Cosmos, Possible Worlds by Anne Druyan. Intelligent Life in the Universe, annotated by Carl Sagan. Lucky Planet by David Waltham. How to Find a Habitable Planet by James Casting. Distant Wanderers by Bruce Dorminey. Interstellar and Extraterrestrial by Avi Loeb. Both of these books I plan to discuss in an upcoming episode very soon, so stay tuned. Again, you can find a complete list of all sources cited, including the many websites that I read, in the description of this episode. So that's it. We made it to the end of the first episode of Paranormal Optimist. We discussed the history of questioning whether we are alone in the universe. We talked about why people don't believe in the possibility of extraterrestrial life, as well as why they do. We discussed where to go from here. We talked about how to find life and what proof of basic life and complex life could look like. But now, it's up to you. Are you an optimist or a pessimist? Are we alone in the universe? To close out this topic, our next episode will be an expert interview in which I had the amazing opportunity to discuss these ideas with a member of the scientific community. I bring a lot of enthusiasm to the paranormal table, but there are just certain limitations I will always have as a layperson. I'm a casual fan of science. I'm not someone who's involved in that world through my trade or my employment. It's a great opportunity to hear a different viewpoint, so I highly recommend you check it out. If you have any paranormal experiences you'd like to share and even have featured on the show, please send me an email at paranormaloptimist@gmail.com. If you're a witness, expert, or enthusiast who would like to participate in a future episode, I would love to talk to you. If you're a creator interested in collaborating or would like me to feature your work in some way on a future episode, again, just reach out. I would love to do that. You can currently follow the podcast through various social media platforms, all of which I hate, but I still have linked in the episode description. Thank you so much for tuning in to this first episode of Paranormal Optimist. This show is written, produced, and presented by me, and my name is still Stephanie. A big thanks to Purple Planet Music for offering their content royalty-free for use in this episode. We are, of course, just getting started, but in a more optimistic tone, know this: we are just getting started.